Hello everyone, hope you are doing well. Welcome to this new video in which one we will find a statistical machine learning approach to predict prostate cancer status. So during this video we'll do two main things. First we'll describe our data and do some manipulation on our data, and after that we will fit our model and do some comparison between different models. So about our data, we are dealing with data with 501 variables, one response variable, and 500 covariates with just 79 observations. So about our response variable, it's the categorical response variable with just two factors, 0 and 1. 0 represents a subject without cancer, and 1 someone who is suffering from cancer. So as you can see here, we have a problem because the number of variables is very greater than the number of observations. So it will be important for us to know the predictor which are really the best among all of our predictors. That's why we perform a Kruskal-Wallis statistic. So here we have the plot of our top 9 best predictor. This is the most best predictor according to this statistic, and as the statistic decreasing, we have the other best predictor. Let's have a look on the correlation matrix of these predictors. So here we have a core plot, and based on this core plot, you can see that some variables are highly correlated, and this can create us another problem of multicollinearity. Because I have two variables which are highly correlated, they're likely giving the same information, so it's better for me if I remove one before building my model. We also perform an eigen decomposition of this correlation matrix, and we get a ratio equal to 17, which is a big number. So let's now start building our model, starting with classification tree with different parameter, different CP. CP means complexity parameter. So here you have a model with CP equal to 0, here a model CP equal to 0.05, and here model CP equal to 0.1. First remark is that the variables on the root of all of these three is among our top 9 best predictor according to Kruskal-Wallis test statistic. And another remark is that when I consider CP equal to 0.05 and CP equal to 0.1, I have no amelioration, no change in my tree. Now let's try to compare this model with another kind of model, KNN. So using now a KNN with different parameters, different value of my K, especially K equal 1, 7, and 9, and this ROC curve on the training set. So based on this, we can see that 1NN seem perform better than all of the others, but we know that for K equal to 1, we are dealing with a more complex model, so we have a risk of overfitting. 1NN take out, we have the trees which are the best, and after that we have the model 7NN and 9NN, which seem like the bad model, the worst model according to this graph. But here we cannot trust this conclusion because it's on the training set. It means that I use the same data to train and test my model. So let's perform again all of this model, and now on the test set, and we get this boxplot. To interpret this, we can say that basically all of the KNN model are performed better than all of the three, which is not exactly what we found based on the ROC curves. Another conclusion or another remark is that between the KNN model there is no significant difference, and between the three I have also no significant difference. So as conclusion, we can say that first, we can perform a Kruskal-Wallis test statistic to test to have the best predictor variables in the whole data, and after that, for this data set, the KNN machine seem like perform better than the trees. And another last remark is that there is no significant difference in the predictive merit of 1NN, 7NN, and 9NN. But you know that in practice we will choose 9NN or 7NN because K equal 1 means that the model is very complex, and if I can do something with I can do the same thing with another model which have less complexity, it will be better for me to choose it. So this is the end of this video. If you have any question, any remark, don't hesitate